and thanks for joining me in a more advanced discussion of single replacement reactions, more advanced than, say, you would typically see in a 10th grade class, although a rigorous 10th grade class may cover it in this level. So when we talk about single replacements, we have an element and a compound forming a new element and a new compound. So an element that had an oxidation number of 0 is going into a compound where it is no longer 0. An element inside the first compound with an oxidation number that was not 0 is coming out to have an oxidation number that is now 0. So whenever you have an element coming into or out of a compound, you have a redox. So single replacement are always redox reactions. Okay, and there's a variety of types, and how active they are. You would either be given an activity series. I don't know many people that would ask you to memorize the metals. The halogens, yes, because it's from the periodic table. But they wouldn't ask you to memorize the metals typically. Or you would be asked to interpret data. And that's what I focus on in my advanced classes is data interpretation. But we could have a metal plus an ionic compound, active metals plus water, like sodium and potassium, those types of metals. Active metals plus hydrogen, or everything above hydrogen on the activity series will react with an acid. A halogen plus an ionic halide. And like I said, these are a simple example of redox reactions. A few little tips that can be helpful here. Don't forget your diatomics. There's a variety of ways to memorize them. I bring clay for our new house. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen are all diatomic. Now, if you have iron and it's going to go into a new chemical, so if I have solid iron and it's going to react in a single replacement, the question is, does it become iron 3 plus or does it become iron 2 plus? Copper, will copper become copper plus 2 or will it become copper plus 1? Lead, will lead become plus 2 or plus 4? And there's a little phrase that I learned when I first started teaching high school. As Snoopy fell, huge cups cracked. As is arsenic, SN, Snoopy, is for tin, FELL, that's iron, HG, mercury, Cu in cups, chromium in cracked. All of these go to their higher oxidation number. So iron goes to plus 3, copper goes to plus 2. Lead's not part of this, so lead would go to its lower oxidation. Tin would go to plus 4, for example. And so that's one way to help recognize which direction, which ion is formed when there are multiple ions. So let's take a look at this. Iron shavings, so that's a solid, added to a solution of lead 2 chloride. Now, lead chloride is considered an insoluble salt, but a little bit of it will always dissolve. You'll learn a lot more about that when you get to equilibrium. So this would be a saturated solution in this case. And what we're going to get is iron 3 chloride, and it's aqueous, and then we would form solid lead. Okay, and so for our complete ionic, I'm going to go ahead and we're going to do net ionics to get more practice on these. My cation is lead 2 plus, my anion is chloride, and there are 2 of them swimming away from each other. And actually, this is my quick reminder to myself that I did not balance. So I need a 3, and I need a 2, and a 2, and a 3. There we go. And so actually I have 3 of these, and I have 6 chlorides, not 2 chlorides. 2 per lead chloride, but that 3 in front gives me 6 chlorides. I'd have 2 iron 3 plus. I'd have 6 chlorides, and then 3 leads. Whoops. Okay, so chloride is my spectator ion, so it could have been nitrate. Same reaction would have occurred. Probably better because lead nitrate's soluble, has a higher solubility. I still like to throw these in every once in a while just to give you an indicator that there are really no absolutes in chemistry. Okay, keep writing, missing my P there in lead. There we go. All right. A piece of sodium is added carefully to water. So I have sodium solid plus water. I like to write that as HOH. I'm going to get sodium hydroxide, aqueous, and hydrogen gas. Okay, so sodium wants to be +1. The OH in water, you can think of it, don't write it this way, but you can think of the OH in water as reacting, okay, in that fashion. I need a 2 and a 2 and a 2. And the complete and the net ionic are actually the same here. Don't dissociate your water. It does not dissociate to any extent. I've got sodium ion and I have hydroxide ion and I have 2 of each. Don't decompose, dissociate, okay? And my net ionic is the same and I don't have any spectator ions for this one. Okay, so I've got a piece of zinc added to hydrochloric acid, mossy zinc, plus hydrochloric acid. Hydrochloric acid is one of your strong acids that you would memorize. So zinc wants to become zinc +2, so it's going to go with the negative chloride. We'll have 2 of those. That's aqueous. Look at your solubility rules. Hydrogen gas. Okay. I'm going to dissociate my strong acid into its cation and anion. This number in front tells me I get 2 H pluses, 2 Cl minuses. The zinc dissociates because it's soluble. Zinc, 2 pluses, the cation, chlorides, the anion. Because of that 2, I get 2 chlorides plus hydrogen gas. Chloride's the only one that shows up the same on both sides, and you would want to rewrite it, not just cross off. If you're asked for a net ionic, you need to rewrite the reaction. I just put that gas there. This would be a solid, this would be aqueous, and this would be aqueous if you were asked for the states. AP doesn't typically ask for states, but that's really up to your instructor. Okay, I think I've done enough of those. I'm going to actually skip that example that's in there. I'll leave that for your own purposes, but I do want to analyze this data for you. Okay, the following reactions are thermodynamically favorable, and we want to rank the different metals. We've got zinc, we've got copper, we've got calcium, and we want to rank them based on the data. So nitric acid and hydrochloric acid, yes, they are both strong acids, but nitric acid is also what's called a strong oxidizing acid. It does more than just a simple single replacement. In fact, the copper penny lab is one of my favorites. So in this case, copper does react with nitric acid, but hydrochloric acid, it doesn't. So if you could put hydrogen on an activity series, it's very likely that copper is below hydrogen because it does not result in a chemical reaction. Calcium, on the other hand, gas bubbles show up. So calcium reacts with water. If we hear this pop, kind of like a barking chihuahua, that popping sound tells us that hydrogen gas was formed. A blue base tells us we must have made, if litmus paper turns blue, we must have made a base. So that's clear indicator that calcium reacts with water. So calcium is going to be way above hydrogen. Okay, we know copper doesn't react with water. I mean, you shouldn't need data to give you that logic that if pennies get wet, they don't dissolve in your pocket, right? We used to dive for pennies all the time in swimming pools. They don't dissolve in water. So we knew that. Hydrochloric acid is poured over zinc. Hydrogen gas collects. So zinc does react with acid. So we know it's above hydrogen, but it doesn't react with water, so it's below calcium. So what we have here is that calcium is more active than zinc, which is more active than copper. And that's the approach that you're going to need to use if you don't have an activity series. Instead, you are asked to interpret data. So a lot of fun different ways you can get data and information on single replacement reactions. So good luck with those types of problems, and thanks for joining me.